And everyone can hear me now, both in the room and virtually. Yeah, so in this lecture, we're going to focus mostly on background material involving population models, branching, and coalescence. I'll introduce a couple of classical population models, and I'll explain how their genealogy can be described by a process called Kingmans Coalescence. I'll then introduce a larger collection of coalescent processes known as coalescence multiple mergers. Next, I'll show how coalescence with multiple mergers can be used to describe the genealogy of certain processes known as continuous state branching processes. And at the end, I will introduce two different population models involving selection, and I'll indicate how they can be approximated by using branching Brownian motion. And then the remaining 4 lectures will be mostly devoted to an in-depth study of those population models, and in particular, the branching Brownian motion approximations. We'll begin with a simple population model. This is the classical Wright Fisher model, which goes back to the work of Fisher in 1921 and Wright in 1930. We assume that the size of the population is fixed, and we'll denote the number of individuals in the population by 2n. This is a discrete time model, and we assume that generations do not overlap. So at every time step, we get a new set of 2n individuals to form the next generation. And we assume that each member of the population has one parent in the previous generation, and to identify the parent, we simply allow each individual to choose its parent uniformly at random from the individuals in the previous generation. And so here's a picture in which we have a population of size 6, just looking here at 2 generations. So this first individual chose the first individual in the previous generation as its parent. These 2 individuals chose this individual as its parent. These 2 individuals chose this individual as its parent, as their parent. And finally, the last individual chose the last individual in the previous generation as its parent. So that's what the Wright Fisher model looks like. Now, in biology, there is a distinction that's made between haploid populations in which individuals have one parent and diploid populations in which individuals have 2 parents. The Wright Fisher model is set up as a model of a haploid population because individuals are assigned only one parent. However, in diploid populations, chromosomes come in pairs, and individuals inherit one chromosome in each pair from the mother and one chromosome in each pair from the father, so that a particular site on the chromosome really does have just one parent. And therefore, the Wright Fisher model is relevant for modeling diploid populations as well, as long as we interpret the 2n members of the population as being the 2n chromosomes of n diploid individuals. And in fact, that's why we usually use 2n rather than n for the population size. Now, the Wright Fisher model describes how the population evolves going forwards in time, but many problems in population genetics are best described or most easily solved by tracing ancestral lines going backwards in time. So now I want to define the ancestral processes. Let's say we take a sample of lowercase n individuals from the population in some generation, let's just say generation 0, and then we're going to trace their ancestral lines backwards in time. So we will let psi n of k be the partition of the integers 1 through n, such that 2 integers I and j are in the same block of the partition if and only if the ith and jth sampled individuals have the same ancestor when we go k generations back in time. And so here's a picture where we have a population of size 6, and we've sampled these 4 individuals from the population in generation 0. None of them have common ancestors in generation 0, so psi n of 0 consists of the partition of 1 through 4 into singletons. Now, if we look 1 generation back, the individuals 3 and 4 have the same parent, so psi n of 1 is this partition where the integers 3 and 4 are in the same block. If we go 2 generations back, the individuals 1 and 2 now also have a common ancestor. And so psi n of 2 is this partition which consists of these 2 blocks. And then finally, when we get 4 generations back, all 4 individuals that were sampled are traced back to one common ancestor. And so psi n of 4 is the partition in which all 4 of these integers are in the same block. Now we want to think about how these ancestral processes should behave. And let's first think about a simple case where we're just tracing back the ancestral lines of two individuals that are sampled from generation 0. Because individuals choose their parent uniformly at random, the probability that these two individuals have the same parent in the previous generation is 1 over 2n, and therefore the probability that they have different parents is 1 minus 1 over 2n. Let's let capital T be the number of generations that we have to go back before we find that these two individuals have the same ancestor. And then the probability that T is bigger than K is the probability that the two individuals that we're following pick different ancestors K generations in a row, and that's going to be 1 minus 1 over 2n to the power K. So in particular, the probability that T is bigger than 2n times x is going to be 1 minus 1 over 2n to the power 2n times x, which as n goes to infinity converges to e to the minus x. And so in particular, we see that T over 2n will have approximately an exponential distribution with rate 1. Notice also that if we were tracking 3 individuals, the probability that all 3 have the same parent in the previous generation is 1 over 2n squared, which when n is large is much smaller than the probability that 2 out of the 3 individuals have the same parent. And so it's rather unlikely that we're going to see 3 or more ancestral lines merging simultaneously. So that description indicates that the genealogy of the population in the Wright Fisher model should be described by a process known as Kingmans Coalescence, which was introduced in this famous paper of Kingman in 1982. Kingmans Coalescence is a continuous time Markov chain. It takes its values in the set of partitions of the integers 1 through n. It starts at time 0 from the partition of the integers 1 through n into singletons. And then as the process evolves, any possible transition that involves 2 blocks merging into 1 is happening at rate 1. And these are the only transitions that are possible. So for example, if at some time there are k blocks of the partition, then there are k choose 2 possible ways to pick 2 blocks that could merge. And so the time until the next merger is exponentially distributed with a rate of k choose 2. And then at the time of the next merger, one can pick 2 blocks at random and merge them together. So the picture of Kingmans Coalescence looks something like this diagram. Here are the 5 individuals that we have sampled. As we trace their ancestral lines back in time, first lineages 4 and 5 merge, then 1 and 2 merge, then 3 merges with 4 and 5, and finally the last 2 lineages merge, and at that point we've traced the entire sample back to 1 common ancestor. And notice that 1 time unit in Kingmans Coalescence corresponds to 2n generations in the Wright Fisher model. So here's a limit theorem that summarizes this discussion. Let's suppose we have a population that evolves according to the Wright Fisher model with a population size of 2n. We'll sample lowercase n individuals at random from the population in generation 0, and we'll trace their ancestral lines back in time. So psi n of k is the partition of 1 through n, such that the integers I and j are in the same block of the partition if and only if the ith and jth sampled individuals have the same ancestor in generation minus k. And then as the population size goes to infinity, the finite dimensional distributions of these processes, not just the finite dimensional distributions, but in fact, these processes psi n converge as n goes to infinity to Kingmans coalescent. And here by this convergence, we mean the weak convergence of stochastic processes with respect to the Skorohod topology. Now, the Wright Fisher model is one of 2 classical population models on which much work in mathematical population genetics has been based. The other is the Morin model, which goes back to 1958. So once again, the population has fixed size 2n, but this model is formulated in continuous time. So each individual independently lives for an exponentially distributed time with rate 1, and then it's replaced by a new individual. And if a new individual is born at time t, then we choose a parent at random from the population immediately before time t to be the parent of a new individual that's born at that time. And with these dynamics, the process can be defined for all real times both positive and negative. Now, it turns out that Kingmans Coalescence exactly describes the genealogy in the Moran model. Here's a theorem to that effect. Suppose we take a sample of lowercase n individuals at random from the population at time 0. We let psi n of t be the partition of 1 through n, whose blocks correspond to groups of individuals in the sample that have the same ancestor at time minus t. And then this process that we get, speeding up time by a factor of n, is exactly Kingmans Coalescence. And the way to see this is to notice that because each individual dies at rate 1, if we're following 2 ancestral lines, the rate of birth and death events along, the rate at which we'll see birth and death events along one of the lineages that we are following is 2. And at the time of that birth and death event, the probability that the new individual that's born comes from the other lineage that we're following is just 1 over 2n. So multiplying them together, we see that 2 lineages in the Moran model are merging at rate 1 over n, and that becomes rate 1, as in Kingmans Coalescence, after we speed up time by a factor of n. Now, Kingmans Coalescence describes the genealogy of populations under a wide range of circumstances. But there are also times when it's useful to consider a wider class of coalescent processes known as coalescence with multiple mergers, or lambda coalescence. And these coalescent processes were introduced independently in 1999 by Pittman and Sagetov, and they also appeared around the same time in work of Donnelly and Kurtz. And these processes have the property that many ancestral lines can merge at once. So we could get a picture like the one illustrated here, where the lineages 1 through 4 all merge at the same time, and then later the last lineage joins them. Now, when might the genealogy of a population look like this? Well, one possibility is that we could have a population in which there are very large family sizes. In that case, many ancestral lines could be traced back to the one individual that had an unusually large number of offspring. Another possibility, which is the one that we will focus on in these lectures, is natural selection. If one individual acquires a beneficial mutation, which is then able to spread to a significant fraction of the population, many ancestral lines could be traced back to that one individual that got a beneficial mutation. Now I want to define the lambda coalescence. Here, lambda is a finite measure on the unit interval. And the lambda coalescence is a continuous time Markov chain, taking its values in the set of partitions of 1 through n, such that whenever there are B blocks, each possible transition that involves k of those blocks merging into one block is happening at a rate that's given by this integral here. Now, the best way to understand the lambda coalescence is to see how to construct it from a Poisson point process. So we can write any finite measure on the unit interval as being the sum of an atom at 0 of some size a, plus some other measure lambda 0, which assigns no mass to 0. And then the lambda coalescence has 2 kinds of transitions. So each transition that involves 2 blocks merging into 1 is happening at rate a. Those are like the mergers that we get in Kingmans coalescence. But then we have these larger mergers that happen at times of a Poisson point process on the positive reals cross 0, 1. The intensity of this Poisson process in the time coordinate is Lebesgue measure, and in the second coordinate is given by p to the minus 2 lambda 0 dp. And then if t comma p is a point of this Poisson process, then we have a so-called p merger at time t, which means that we flip an independent coin for each lineage, which comes up heads with probability p, and we merge all the lineages whose coin comes up heads. And so the measure lambda is really governing the rates of p mergers for various values of p. Now, I want to give an example of a population model whose genealogy is best described by a coalescent with multiple mergers. And here's an example involving a population with a heavy-tailed offspring distribution. So let's consider a model where, once again, the size of the population is fixed. We'll say there are n individuals in the population. As in the Wright Fisher model, generations do not overlap. And we'll assume that the numbers of offspring of different individuals in the population are IID random variables taking their values in the set of positive integers. And then we're going to assume that the offspring distribution has this tail behavior here. So the probability that an individual has k or more offspring will be asymptotic to a constant times k to the minus alpha, where alpha is at least 1. Now, this process will likely produce more than n offspring, but the population size has to stay fixed at n. So we will obtain the next generation by sampling n of these offspring without replacement. And that could be somewhat realistic if the population, if the environment can only support a population of a certain size. And then we can define the ancestral processes as before. We can sample lowercase n individuals from the population in generation 0, and we can let psi n of k be the partition of 1 through n, whose blocks correspond to groups of individuals in the sample that have the same ancestor when we go k generations back. Yes?
One question. I mean, so it's likely because of the heavy tail that we will have more than n individuals, but it could technically happen that we have less than n, right?
Well, yeah. So in the paper, we actually deal with that case. It could happen that you have less than n. The way I've defined it here, though, they're positive integers. So I just sort of wiped out that case. There are somehow better ways to deal with that case that can allow it in certain conditions, but here I just wanted to take that off the table.
Everyone has at least one offspring, and then we'll always have at least n.
Right. You'll have at least n by the way that's defined. Okay, so what can we say about the genealogy of the population as n tends to infinity? Well, if alpha is greater than or equal to 2, then large families are sufficiently rare that, just as in the Wright Fisher model, the genealogy of the process is described by Kingmans Coalescence. However, if alpha is between 1 and 2, then large families happen more often. And as a result of that, we can get multiple mergers of ancestral lines. And the genealogy is best described by the beta coalescent with parameters 2 minus alpha and alpha. So it's the beta coalescent, and by that I mean the lambda coalescent, where lambda has the beta distribution with parameters 2 minus alpha and alpha. If alpha is equal to 1, well, the beta 1,1 distribution is uniform on 0, 1, and the lambda coalescent, where lambda is the uniform distribution on 0, 1, is called the Bolthausen-Snittmann coalescent, and it's the Bolthausen-Snittmann coalescent that describes the genealogy when alpha is equal to 1. It's useful also here to look at the time scaling. In the case when the offspring distribution has finite variance, so that happens when alpha is greater than 2, the probability that 2 individuals have the same ancestor in the previous generation is of order 1 over n, and so we have to speed up time by a factor which is of order n, just as in the Wright Fisher model. When alpha is between 1 and 2, because large families happen more often, it's more likely that 2 individuals choose the same parent or have the same parent, and therefore we only have to speed up time by a factor of n to the alpha minus 1. If alpha is equal to 1, large families are even more prevalent. The probability that 2 individuals have the same parent is of order 1 over log n, and so we're only speeding up time by a factor of log n. Now, I want to comment on why the beta coalescent describes the genealogy in this model, and I'm going to focus on the case where alpha is between 1 and 2, so that the offspring distribution has finite mean, which I'll denote by mu. Now, let's suppose that some individual has psi offspring, perhaps an unusually large number. Then the other n-1 individuals, by the strong law of large numbers, are likely to produce roughly n times mu offspring. So the fraction of the population descended from the individual that had psi offspring is going to be roughly psi over psi plus n times mu. Let's call that number p. Then, as we are tracing back ancestral lines, notice that we are going to get a p merger around the time that that large family appears, because roughly a fraction p of the ancestral lines go back to that one large family, and therefore they're going to merge at that time. So we're going to get a p merger with p greater than or equal to x if psi over psi plus n times mu is greater than or equal to x, or equivalently, if psi is at least x over 1 minus x times n mu. Now, we can calculate the probability that that happens in a particular generation. It's the number of individuals n times the probability that a particular individual has at least this many offspring, which is a constant times this number to the power minus alpha. Now, in the lambda coalescence, we have p mergers at the rate p to the minus 2 lambda dp. So to find the rate of p mergers with p greater than or equal to x, we have to integrate p to the minus 2 lambda dp. For the beta coalescent, that means we integrate p to the minus 2 times the beta density. And if you do a little calculation, you get this constant times x over 1 minus x to the minus alpha. And so the fact that we get this same form in both calculations tells us that after a time change, the genealogy in the population model is going to be described well by the beta coalescent. All right, so up to this point, we have seen some classical population models whose genealogy is given by Kingmans Coalescence. We've also seen a population model with large family sizes whose genealogy is described by a coalescence with multiple mergers. What I want to do next is to work towards explaining how we can describe the genealogy of continuous state branching processes. That requires a bit of background and setup. I want to begin with a very brief review of BBM, Galton, Watson processes. Let's say we have a sequence of non-negative numbers that sum to 1. And then we can consider a population that has the following properties. So typically we start with one individual in generation 0. The probability that an individual has k offspring is given by p sub k, and the numbers of offspring of different individuals are independent of one another. So then we can let z sub n be the population size in generation n, and then this process Zn is called the BBM Galton Watson process with offspring distribution pk. I'm going to let L be a random variable which equals k with probability p sub k. So L has the same distribution as the offspring distribution for the branching process. We'll let M be the expected value of L, and we say the process is subcritical if M is less than 1, critical if M is equal to 1, and supercritical if M is bigger than 1. And as you probably know, if the process is critical or subcritical, then the population dies out with probability 1. If the process is supercritical, then with positive probability, the population survives forever. The only exception is the trivial case where P1 is equal to 1. Then every individual has exactly 1 offspring. We have 1 individual in every generation, and the process is critical, but it does survive forever. Now, I want to mention here a few other famous results related to BBM Galton Watson processes. First, let's consider the critical case. So the offspring distribution has mean 1 and finite variance sigma squared. In 1938, Kolmogorov proved a result about the probability that the process survives for an unusually long time. He showed that as n goes to infinity, the probability that the process survives for at least n generations is asymptotically 2 over n times sigma squared. And later, Yaglom showed that conditional on the event that the process survives for n generations, the number of individuals in generation n is of order n, and the conditional distribution of Zn over n, given that the process survives n generations, converges to the exponential distribution with a mean of sigma squared over 2. One can also consider the supercritical case where m is bigger than 1. The expected size of the population in generation n is then m to the n. And if we take Zn over m to the n, that process gives us a martingale. It's a non-negative martingale, so the martingale convergence theorem tells us that it converges to a limit, which we will call W. And notice that unlike in the classical strong law of large numbers, this limit W has to be a random limit. Because, for example, if the initial individual had 2 offspring in the first generation, then on average W would have to be twice as large as it would be if that initial individual just had one individual in the one offspring in the first generation. Now, so one can ask when this random variable W is strictly positive, and the answer is given by the famous L log L criterion due to Keston and Stigam. As long as the expected value of L log L is finite, this limiting random variable W is positive almost surely on the event that the process does not go extinct. However, if the offspring distribution is sufficiently skewed that it has finite mean, but the expected value of L log L is infinite, then the random variable W will be zero when the random variable W will be zero almost surely. In that case, Seneta and Heidi showed that we still can get a non-trivial limit under a different scaling. There exists a sequence of constants Cn such that if we take Zn over Cn, then almost surely on the event of non-extinction, that will converge to a limit which is strictly positive and finite. Now, we also need to introduce Lévy processes, which are stochastic processes with stationary independent increments. A process X is called a Lévy process if it satisfies these three conditions. So if we have some positive numbers T0, T1, and so on up to Tn, then the increments x of T1 minus x of T0, x of T2 minus x of T1, and so on up to x of Tn minus x of Tn minus 1 are independent. So the way that the process moves in different increments of time, those movements are independent of one another. If s and t are positive numbers, then x of t plus x, x of t plus s minus x of t has the same distribution as x of s minus x of 0. So that's the stationarity of the process. And then we also assume that the process is right continuous. Not hard to come up with examples of Lévy processes. So one example is standard Brownian motion. Then the characteristic function of the random variable x of t, which represents the position of the Brownian particle at time t, is e to the minus 1/2 u squared t. A trivial example of a Lévy process is deterministic drift at rate d. And then x of t is exactly d times t. So the characteristic function is e to the I times d times u times t. And a third example would be if jumps of size x happen at times of a rate lambda Poisson process. So the process jumps up by x at these times, at these jump times that happen at rate lambda. And then a short calculation tells us what the characteristic function should be in that case as well. The main result about Lévy processes is the famous Lévy-Hingen theorem, which basically tells us that every Lévy process is in some sense a mixture of those three. So suppose X is a Lévy process, and without losing much generality, we can assume that it starts at 0. And then there's a function phi called the characteristic exponent, such that the expected value of e to the iu x of t, so the characteristic function of x of t, is given by e to the t times phi of u. Phi has this expression here. So here d is a drift. Sigma squared is the variance of a Brownian component. And nu is a so-called Lévy measure, which governs the jump rates for the process. So if nu were a unit mass at x, then the process would jump up by x at times of a rate 1 Poisson process. But in general, nu could be a diffuse measure, and then we could get jumps of all different sizes. Now, if the Lévy process has no negative jumps, then we can work with the Laplace transform instead of the characteristic function. In particular, the expected value of e to the minus lambda times x of t is given by e to the t times psi of lambda, where psi of lambda looks pretty similar to the formula that we had before. The main difference is that because negative jumps are no longer allowed, the measure nu governing the jump rates for the process is concentrated on the positive real line. So we're now ready to introduce continuous state branching processes. And continuous state branching processes can be viewed as the continuous analogs of BNMA Galton-Watson processes. So a continuous state branching process is a continuous time Markov process, and it takes its values on in the set of non-negative real numbers. And the transition functions have to satisfy this branching property here. So we get the same distribution if we start from A plus B and run the process for time t as what we get from running two independent copies of the process for time t, one started from A and one started from B, of adding them together. So here we're thinking of x of t as representing the size of a population at time t. I'll refer to real numbers between 0 and x of t as being individuals in the population at time t. And this branching property is capturing the idea that individuals in the population are behaving independently of one another. And in fact, Lamperti showed that continuous state branching processes are precisely the processes that can arise as limits, as scaling limits of Galton-Watson processes, when we allow the initial population size to go to infinity and then do the appropriate scaling to get a limit. Now, Lamperti also gave another characterization of continuous state branching processes. So let's let Y be a Lévy process with no negative jumps, which starts at 0, starts at some positive value and is stopped when it hits 0. And then this process X, which we get through this time change of the Lévy process, is a continuous state branching process. And furthermore, every continuous state branching process can be obtained by time changing a Lévy process. And this should make sense because the individuals in the continuous state branching process are behaving independently of one another. And so the process should evolve like a Lévy process with stationary independent increments, except that if the population size doubles, changes in the population will occur twice as fast. And so we need to do this time change to make the time run at a speed proportional to the population size. Negative jumps are prohibited because negative jumps would mean that many individuals die at once, which contradicts the idea that individuals behave independently of one another. On the other hand, positive jumps are allowed because one individual could have a large number of offspring all at once. Now, suppose X is a continuous state branching process, which is obtained by time changing the Lévy process Y. Well, then we can write the expected value of e to the minus lambda times y of t in this usual Lévy-Hintgen form, where d is a drift, sigma squared is the variance of a Brownian motion component, and nu is a Lévy measure, which governs the jump rates for the process. And this function psi is called the branching mechanism of the continuous state branching process. So let's look at a few examples of continuous state branching processes. So if the branching mechanism is given by 1/2 times lambda squared, then this process is known as Feller's branching diffusion. This is the process that we get by time changing, Brownian motion, and it happens to satisfy this stochastic differential equation here. And we can see that the process is moving more quickly when the population size is larger. These other two examples are processes with jumps. And the best way to understand the jumps is to look at the Lévy measure. So if alpha is between 1 and 2, then we can consider the continuous state branching process whose branching mechanism is given by lambda to the power alpha. And this is known as the alpha stable continuous state branching process. And here we can see from the Lévy measure that jumps of size x are happening at a rate proportional to x to the minus 1 minus alpha. Now, to take alpha equal to 1, so that jumps of size x are happening at a rate proportional to x to the minus 2, that leads to a continuous state branching process whose branching mechanism is given by lambda times the log of lambda. And this process was first studied in 1992 by Neveu. So now, because we can view a continuous state branching process as modeling a population, we want to be able to define the notion of a genealogy of a continuous state branching process. Now, this is a rather delicate issue, and I'm not going to describe all of the technicalities, But basically, there are two ultimately equivalent approaches. One approach, based on work of Bertrand and Legal, is to construct this three-parameter process here. So the process SST of A is a stochastic process which describes the evolution of the population between time s and time t. And we can interpret SST of A as being the number of individuals at time t that are descended from the first A individuals in the population at time s. And so then if y is an individual in the population at time t, so that means y is a number between 0 and x of t, then we can identify its ancestor in the population at time s to be the infimum of the set of all b's, such that SST of b is bigger than or equal to y. So basically, this is how big the population size would have had to have been at time s in order for there to be at least a population size of y at time t. Now, the alternative method is based on the celebrated look-down construction of Donnelly and Kurtz. Their idea was to represent the population by a countable system of particles, which is indexed by the positive integers. And that makes it possible to describe the genealogy of a sample of size n by simply looking at the particles labeled 1 through n and directly following their genealogy. What is known about the genealogy of continuous state branching processes? Now, in the case where the continuous state branching process is given by Feller's branching diffusion, results of Perkins in 1991 tell us that after a time change, the genealogy can be described by Kingmans Coalescence. The reason why a time change is needed is that when we identified Kingmans Coalescence as describing the genealogy in the Wright Fisher model, we had to speed up time by the population size 2n. But in the case of Feller's branching diffusion, the population size is variable, so this brings about a non-trivial time change. In 2000, Bertrand and Legal showed that for Nevers' continuous state branching process, the genealogy can be described, this time without a time change, by the Bolthausen-Schnittmann coalescence. And then a few years later, there was this paper of 7 authors who showed that if the continuous state branching process has no Brownian motion component, and the density of the Lévy measure is proportional to x to the minus 1 minus alpha for alpha between 0 and 2, then after a time change, the genealogy of the population is described by the beta coalescent with parameters 2 minus alpha and alpha. Notice that when alpha is equal to 1, the beta 2 minus alpha alpha coalescent is, well, that's the beta 1, 1 distribution, which is uniform on 0, 1. And so we recover the result of Bertrand and Legal that the genealogy is given by the Bolthausen-Schnittmann coalescence. Now, it's useful to compare these results to the results that we got in the model of a population of a fixed size n, in which the numbers of offspring produced by different individuals were independent. Feller's branching diffusion is what we get when we take a limit of critical Bienemé-Galton-Watson processes whose offspring distribution has finite variance. And Kingmans Coalescence described the genealogy of Feller's branching diffusion, just as it did in the previous model in the case when the offspring distribution had finite variance. Also, when alpha is between 1 and 2, the alpha stable continuous state branching process is what we get when we take a limit of critical Bienemé-Galton-Watson processes whose offspring distribution has this tail behavior. And so it shouldn't be surprising that the beta coalescent describes the genealogy in both cases. So I do want to describe briefly where this result about the genealogy of continuous state branching processes comes from. I'm going to focus on the case where the Lévy measure has a density proportional to x to the minus 1 minus alpha. And we'll let A be the current population size. That is the current value of the process. Now, let's say that at some time, this continuous state branching process makes a jump of size x. So then after this jump, the fraction of the population that was just born, which I will call P, is x over A plus x. And so if we trace ancestral lines backwards in time, we're going to see a p merger around the time of this event, as roughly a fraction p of the ancestral lines merge, because we presume that that jump in the continuous state branching process resulted from one individual having a large number of offspring. So we get a p merger at the time of that event. Now notice that x over a plus x is greater than or equal to r if and only if x is greater than or equal to a times r over 1 minus r. And so we get p mergers with p greater than or equal to r whenever there is a jump in the continuous state branching process of size greater than a times r over 1 minus r. And so to find the rate of those events, we observe that the rate is proportional to the size of the process A, and then we multiply that by the Lévy measure from a times r over 1 minus r to infinity. And we end up getting this constant times a to the 1 minus alpha times r over 1 minus r to the minus alpha. But we already saw when working with the population model of fixed size that the rate of p mergers with p greater than or equal to r in the beta coalescent is given by this expression here. And so what we can see is that if we speed up time in the continuous state branching process by a to the alpha minus 1, then the genealogy is going to be described by the beta coalescent. When alpha is equal to 1, this a to the 1 minus alpha goes away. And so that's the case of the Bolthausen-Snettmann coalescent, where no time change is needed. All right, so at this point, we have seen several different population models. We've seen classical population models whose genealogy is described by Kingmans Coalescence. We've seen populations with large family sizes, both a discrete time model as well as continuous state branching processes, whose genealogy can be described by a Lambda coalescence. But up to this point, we have not discussed natural selection, which is going to be the main subject of these lectures. So I want to end these lectures by introducing two different population models that involve selection, and these will be the main focus of the remaining 4 lectures. So this first model was introduced by Brunet, de Rita, Mueller, and Meunier. Here we assume that the size of the population is fixed at capital N. As in the Wright Fisher model, we assume that generations do not overlap. We assume that each individual has k offspring, where k is some fixed integer that's greater than or equal to 2. And then each individual in the population will be assigned a real number, which we call the fitness of the individual. And the fitness of each offspring will be the parent's fitness plus an independent random variable with some distribution, say nu. Now, because each individual has k offspring, this means there are going to be k times n offspring produced, but the population size needs to be fixed at n. And so we say that the n individuals with the highest fitness survive to form the next generation. Now, here's a different population model involving selection. This is basically a Morin model with selection. Once again, we assume that the population has n individuals at all time. But this is a continuous time model, and we assume that each individual independently acquires mutations at rate mu sub n. So mu sub n is the mutation rate per individual. And we assume that all of these mutations are beneficial. So that means we model this by saying that an individual with j mutations at time t has a fitness of 1 plus Sn times j minus m of t, where m of t is the average number of mutations carried by the n individuals in the population at time t. So if an individual has 3 more mutations than average, its fitness will be 1 plus 3 times Sn. So the parameter Sn is measuring the fitness benefit that one gets from a mutation. So then each individual independently lives for an exponentially distributed time with rate 1. And when an individual dies, we choose an individual at random from the population with probability proportional to fitness to be the parent of the new individual that is born. And then the new individual, of course, inherits all of its parents' mutations. And so individuals with higher fitness are more likely to have offspring. Now, the fact that the previous model was formulated in discrete time and this model happened to be formulated in continuous time, has no particular significance. One could have done it the other way around. What is significant is that in this model, individuals with higher fitness are more likely to have offspring, whereas in the previous model, we model selection by killing all individuals whose fitness drops below a threshold. What we want to do is to approximate these two population models using branching Brownian motion. And so we want to define how we do that. So we're going to begin with some configuration of particles on the real line at time 0. And we want to think of each particle as representing an individual in a population. And the position of the particle corresponds to the fitness level of the individual. Now, each particle is going to move according to one-dimensional Brownian motion with a drift of negative rho. And so this movement of the particles represents the change in fitness of individuals as they acquire mutations. Now, to introduce selection, we need to describe births and deaths. And we'll do that a bit differently to approximate the two models. So to approximate model 1, we're going to say that each particle splits into two particles at rate 1. But then we need particles with very low fitness to be killed. So what we'll do is to assume that the particles all start out on the positive real line, but then they're killed if they reach the origin. So once the fitness of the individual drops to 0, the individual is killed. That process is known as branching Brownian motion. It's been studied extensively in its own right, and we can use it to approximate the first of those two population models. Now, to approximate model 2, we're going to use a different variation of branching Brownian motion. We're going to say that each particle dies at rate 1, but a particle located at x splits into two particles at rate 1 plus beta times x. So individuals with higher fitness are more likely to have offspring, just as in the second of those two population models. Now, in order to make this a well-defined model, we're going to need some adjustment here so that when x is less than -1 over beta, the branching rate doesn't go negative, but we'll address that when we return to this model later. So throughout the next 4 lectures, we're going to be studying these two population models, and in particular focusing on these approximations that are based on branching Brownian motion. But I'll stop here for today. Thank you.
So thanks very much. Does anyone have questions for Jason? And also, are there any questions on the Zoom?
Yeah, so it seems a p-merger happens in the limit when you have single individuals that kind of reach a fraction of the population, existing population with their offspring. It seems that happens as soon as the variance was infinite, but that doesn't seem intuitive. Is that right or wrong? Variance of offspring distribution.
It's not exact. It's not exactly that. So let me go back to, yeah, you can have, so in the first case here, when we talked about, right. So notice in the first bullet here, when alpha is greater than or equal to 2, we get Kingmans coalescent in the limit. So when alpha is equal to 2, we do have infinite variance, just barely, and yet we still get Kingmans coalescent. So it takes a little bit more than infinite variance to produce the multiple mergers.
So a little more than that is enough for a single individual to instantly have a fraction of the existing population of this offspring.
Right. It doesn't happen often, but keep in mind here that it only needs to happen once every n to the alpha -1 generations.
Right.
And then that becomes the dominant source of fluctuations.
Good. Thanks a lot.
Or the dominant source of mergers.
Any more questions in the room or on the Zoom?
Yeah.
So I guess as we're sort of already, thanks to the technical issues, running a bit ahead of time, maybe we should move on to the next talk. But let's thank Jason again for his